Okay, let's start the next lecture. So, Alexei Kitaev is awardee of the physics part of the conference. I've known him for about 6 or 7 years. When he visited Harvard CMSA, he was working with Dan Free and Mike Hopkins in those days. And they have some kind of meetings constantly each year, and happens to choose Harvard in my institute, CMSA, and so I met him. He was more quiet than what I thought. I'd like to talk with you more. And I was in the physics department. There was discussion on how to recruit him to come for even just short visit. It was not easy. So I was very pleased when we announced the award to him. He accepted instantly, which I'm really very grateful that he will take this offer to come. And it was really a important event that he will come. And he is expert on quantum computing, one of the founder of quantum computing and statistical physics. Subir has talked about his work on Sunday, so I would not repeat it. But we will listen to his work, which is extremely important today, called Chaos and Black Hole. So, Alexei, thank you.
Thank you for the kind introduction and for the invitation. It's a pleasure to me to speak here in this audience. Um, my talk will be about chaos and black holes. And as you can tell from this picture, it's a kind of toy version of a black hole. So it's a highly theoretical talk discussing connections between different mathematical models. But those models can shed a light on interesting physical phenomena. This is the outline. Chaos is something unpredictable and irregular, but this is not a good definition. We may not be able to predict things because we don't understand them. And a better definition is that chaos is related to fundamental unpredictability. It's like it is impossible to make weather forecast more than for a few days, because a small change in the weather conditions now will be amplified later, and in a month, even a flap of butterfly wings will affect the weather. This is classical chaos, and it's pretty simple. I'll say more about it in a minute, but the main subject is quantum chaos. Quantum chaos is less intuitive. It's described by out-of-time order correlators. We consider the product of operators applied at different times, and those times should alternate. And this way we construct a quantity that is analogous to classical observables and that is sensitive to chaos. There are many chaotic systems, classical and quantum. I'll focus on two systems or classes of systems. One is black holes. This is an image of an actual black hole in another galaxy, in the center of a galaxy that can be seen from Earth using radio telescopes. However, the subject of my talk is related to subtle properties of black holes that are not easily related to observations. Space-time geometry can be related to observations, but there are parts of the black hole that are hidden from sight. Oh, what happened? Oh, it's back. Yeah, thank you. I hope you saw the previous picture. There are part of black holes that are hidden from sight, and in this picture, there is a physical region and some regions inside the black hole, and the boundary between those regions, which is called horizon. Those are not seen directly, but we can study them theoretically. The next picture illustrates Hawking radiation. It's a quantum effect in black holes. As Edward Witten said in his lecture yesterday, Einstein gravity and quantum mechanics do not combine well, and to combine them, one needs a more advanced theory like string theory. However, some simple quantum effects can be studied within the framework of Einstein gravity. They do combine if we don't go to very short distances. And Hawking radiation is one such effect. The other effect is called Dray-Hoof effect. It's both classical and quantum. Classically, if we throw an object into a black hole, it's gone. We never see it again. However, this object creates a perturbation of space-time inside the black hole. And this perturbation can be regarded as a shock wave concentrated in the vicinity of the past horizon. Hawking radiation particles pass through this shock wave, and the state of the radiation is affected by the shock wave. But it's kind of like a butterfly. We cannot detect the presence of a butterfly just looking at the weather around. We don't know whether it rains because of the butterfly or for some other reason. And the same is true of Dray-Hoof effect. I'll explain it later in more detail. The other class of systems that exhibit chaos is large N models, including the Sachdev-Ye-Kitaev model. A large N system is a system of simple degrees of freedom, like spins of fermions interacting with each other. And they interact all to all. Every pair or every group of 4 particles are coupled to each other and interact. This is an illustration. The Sachdev-Ye-Kitaev model is special in that out-of-time order correlators or chaos in that model are similar to chaos in black holes. And this is because the SYK model has a soft mode, a collective mode. We know collective modes in condenser matter systems like sound is a collective mode in a system that is built of atoms. But in this case, the collective mode is more interesting. It's a reparameterization of time. You can think of time as a spring, and I've drawn a circular time, which is imaginary time, so-called Matsubara time. And there is a collective mode that involves deformation of the time spring, and it's also related to geometry. So let me start from the beginning. The butterfly effect. A flap of butterfly's wings can change the weather. We believe this is true because the Earth, with its atmosphere and ocean, is a complex, chaotic system. But it's too complex. Let's consider a simple chaotic system, the stadium billiard. This is a billiard, and this is the trajectory of a ball that bounces off the walls and moves without friction. And you see that the trajectory is kind of irregular. How do we understand that? To understand it, we need to first write down the equation of motion, and those equations can be written in terms of 4 variables. There are 2 coordinates, Q1 and Q2, and the corresponding momenta, P1 and P2. And that whole set of 4 variables is the full description of the system state. The state evolves in time according to some equations, and if we consider 2 trajectories with slightly different boundary conditions, the difference is amplified over time such that the trajectories diverge. You see the red trajectory and the green trajectory diverge, and they diverge exponentially in time. And the exponent kappa is called the Lyapunov exponent. The exponential divergence of trajectories is the hallmark of classical chaos. This is a simple mathematical phenomenon. It can be seen in simulations, but is there a direct way to measure chaos? The problem is the absence of reference data. So I'll pause for a moment and let you think about a way of testing this theory. Okay. There are two tests. Test one, run the Earth's time or the Earth's dynamics forward and backward, and we can describe a particular experiment. Begin the experiment at time 0, advance the Earth's time to t and record weather data. Then we run the time backward, introduce a butterfly, and run the time forward again. And finally, we compare the weather now with the recorded weather without the butterfly. And test 2 is to do the 2 runs in parallel using 2 copies of the Earth. Of course, it sounds ridiculous. That's in part because the Earth is such a big system that we cannot control it. Let's talk about control. This kind of tests can actually be done on small systems, but they require very precise control. If we are to do such a test on a classical system, the required accuracy should be exponential, such that errors in our experiment are smaller than the amplified errors due to the divergence of trajectories. This requirement can be met in a simulation because we can increase the number of precision digits, and we can use the number of digits proportional to the simulation time. In an actual experiment, it's very hard to do. So it can only be done for very short times. But for longer times, the exponential dependence stops and quantum effects become important. For quantum systems, the scaling is more favorable. The required accuracy is n times t inverted. And this number says that there shouldn't be any error at all during the simulation. An error would be, say, 1 photon or 1 phonon absorbed during the simulation. It's a stringent requirement, but it can be met using high-quality qubits or a small system like several nuclear spins in a molecule. Now I would like to discuss quantum chaos. And I need to begin with some introduction of quantum mechanics. I assume that everybody in this room have learned quantum mechanics at some point, but does not necessarily remember it well. So this slide is supposed to serve as a reminder. In quantum mechanics, we have basis states and general states. And I use a system of n spins or n qubits as an illustration. Each qubit can be in state 0 or in state 1. And if there are 2 qubits, there are 4 basis states, 0, 0, 0, 1, 1, 0, 1, 1. And the state vector is a superposition of those states or linear combination of those states with some complex coefficients. Those coefficients should add up to 1 if we square them. The square of a coefficient is the probability of the corresponding basis state. And this is one example of a superposition. One can also describe states by the density matrix. It's an operator made out of the state vector like this. And this description is more convenient because it can be reduced to a smaller system. For example, if we're only interested in the state of the first qubit, we cannot define the state vector of that qubit alone, but we can define the reduced density matrix of the first qubit. tensor product is an important mathematical construction that describes putting two small systems together. We can multiply states like this. We have two state vectors, state vector of the first qubit and of the second qubit, and we can define their product. Not every state of two qubits is the product of states of individual qubits. For example, this state is not a product state. However, we can act on states with operators. And those operators can be multiplied regardless of whether we act on product states or not. For example, we can consider the tensor product of the identity operator and the Pauli matrix sigma z, and we get this. And in physics, the usual notation is sigma z2. 2 means that sigma z acts on the second qubit, or the second spin. An important thing in quantum mechanics is measurement. An experiment is usually set up in such a way that we start with some initial state, evolve it for a certain time period, and the evolution is governed by the Schrödinger equation. The overall state change over the given time period is given by the evolution operator U, and this evolution operator is the exponential of the Hamiltonian. If the Hamiltonian is time dependent, one has to use the so-called time-ordered exponential, but that is not important for my talk. After the evolution is done, we can measure some quantity. There are different types of measurements. A measurement usually gives some number, but let's consider the simplest form of measurement, a yes or no measurement. We could measure, for example, whether the first qubit is in state 1 or in state 0. 1 means yes, 0 means no. We can specify the measurement by specifying a projector. This is a projection operator. And given a state, quantum mechanics states that psi has the following probability of the measurement to find the outcome yes. The probability of the yes outcome is given by the matrix element. We apply the projector to psi and then multiply by psi again. Consider the inner product. It can also be expressed in terms of the density matrix. And the evolution starting from the initial state followed by measurement can be expressed like this. We plug this formula in here and we get the final expression as a trace. And this expression contains something called pi of t. It's the projection operator evolved backward in time to the initial state when we can apply it to the state description rho, which is a density matrix. Now, the probability is a special form of a correlation function or a correlator. And the general notation for correlators is this. If we have some operator A and some state described by the state vector psi or the density matrix rho, we can define A in angular brackets by these formulas. Now, we'll use this notation to describe a simple process and its outcome. We start with initial state psi, then we apply operator x, then we let the system evolve for time t, and after the system has been evolved, the final state is a function of the initial state. And then we can perform the measurement, and the measurement is done in the real world, but we can estimate the probability of the yes outcome on paper, theoretically. And it's given by this formula, which can be expressed as a correlation function. It's the correlator of three operators: x at time 0, the projection describing the measurement at time t, and x dagger at time 0. And all subsequent equations will involve correlation functions. This is the way to describe things in quantum mechanics. Let me introduce a variant of the measurement protocol. We may use an auxiliary qubit for control, for a choice of operators to apply. We start with the initial state psi in the main system and some auxiliary state of the auxiliary qubit. It has parameters C0 and C1, and the auxiliary qubit is used to select between two operators, select x0 or x1, depending on whether the auxiliary qubit is 0 or 1. And the selection process is described by a certain operator that involves both the main system, x0 and x1 act on the main system, and the second parts act on the auxiliary qubit. And we get this state, then we let the system evolve, perform the measurement, and we get a correlation function. The important point is that the correlation function in general contains different indices J and K. So there will be a cross correlator between x0 and x1. That's how cross correlators appear in experimentally observable quantities. They appear when we actually have a slightly bigger system. One can generalize this by introducing a general state that is a product of the system state and a device state. Then we evolve this combined system with the combined Hamiltonian that includes some interaction between the system and the device. And the details here are not important, but in the end, we get some cross correlators that have a very specific structure. This product of operators depends on times, T1, TP, TS prime, T1 prime, and those times occur in a certain order. First, the time increase, we go up, which means we go forward in time, and then the time decrease, we go down. So in a natural measurement scheme, the correlators do not alternate. They involve going forward in time and then backward in time. But there are also out-of-time order correlators that can be defined theoretically. And if we believe in quantum mechanics, such quantities have some meaning. They were first discovered by Larkin and Ovchinnikov in 1969. And back in those times, people did not think about subtle properties of systems of qubits that can be evolved the way we like. People were focusing on real systems or natural systems that occur in nature. And Larkin and Ovchinnikov studied superconductors. And they calculated a certain quantity for a real superconductor, which of course did not contain any out-of-time order correlators. But then they related this quantity to a similar quantity in a normal metal. And the relation is such that out-of-time order correlators appear. This is a mathematical trick. That's how they introduced out-of-time order correlators. But we can also introduce them by thinking about an experiment with a few qubits. We can say metaphorically that we have operators describing where the measurement and where the change or the flap of butterfly's wings, and we observe whether at time t introduce the butterfly at time 0 and observe the weather at time t again, which is described by the product of three operators. First, the observation at time t, butterfly in time 0, observation at time t. And a quantum device can select one observation of the two, and we get a cross correlator like this. It's an out-of-time order correlator. So this is quantum chaos. Now, out-of-time order correlators are related to classical chaos, and that was already observed by Larkin and Ovchinnikov. In classical mechanics, we have Hamiltonian evolution, coordinates and momenta. In quantum mechanics, we have the corresponding operators, Qj, and this operator P sub j is the momentum operator in quantum mechanics, and classical mechanics can be considered as a limit of the classical of the quantum mechanics as h bar goes to 0. And the commutator of two momentum operators is related to the classical Poisson bracket, which is in turn related to the derivative of the final state with respect to the initial state. And if we know that this thing grows exponentially time, we can guess how the commutator depends on time, how the square of the commutator depends on time. And in fact, if we consider the out-of-time order correlator, which is related to the average value of the square commutator, then there will be some constant term plus or minus some correction that grows exponentially in time. And it will grow until the whole quantity approaches 0. When it approaches 0, then quantum effects become strong. We can no longer use the correspondence between classical and quantum mechanics, and we have to solve the full quantum problem. So this is OTOC in a semi-classical system. It turns out that many quantum systems that do not have a natural h bar going to 0 limit exhibit similar behavior. For example, quantum fields in the vicinity of black hole exhibit this behavior of the out-of-time order correlator. The out-of-time order correlator minus a constant grows exponentially in time. The coefficient in front is small. The S in the denominator is the entropy of the black hole, which is huge. So this quantity is very small at first, but then it becomes large. And when the right-hand side is of the order of 1, the formula is no longer applicable. The exponential growth saturates. But a peculiar feature of black holes is that the Lyapunov exponent has a well-defined value. It's related to T, which is the Hawking temperature, which I will explain in a moment. So black holes have out-of-time order correlators behaving similarly to a semi-classical system, but instead of h bar, we have a small parameter 1 over s. Non-integrable large N systems with all-to-all interactions exhibit similar behavior. And the small parameter is 1 over n. Here, the situation with the Lyapunov exponent is more complex. In most examples, the Lyapunov exponent is small, which means that the dynamics is slow. In general, the dynamics cannot be arbitrarily fast. This number 2 pi times the temperature in dimensionless units is the upper limit. It was shown by Schenker, Stanford, and Maldacena in 2015. The dynamics cannot be faster than that. Black holes have chaotic dynamics as fast as possible. But there are some examples of large N systems which approach that limit. In particular, the SYK model has the Lyapunov exponent that is close to the maximal value, and the correction is small when the temperature is small. As the temperature goes to 0, the correction becomes negligible. So this is the main message. The message is that black holes and the SYK model have similar out-of-time order correlators. In particular, the Lyapunov exponent is the same, and maybe there is some deeper analogy between these two systems. Now, let me accelerate a bit. I'll talk about black holes and then the SYK model. And this is slightly more technical. This slide, of course, is not technical. It's just an introduction into black holes. We can estimate the mass and the radius of a body which will look black in the following way. We can try to send light from the surface of that body to the space, and instead of sending light, let's first throw a ball. A ball with mass m is thrown with the velocity v, which is the escape velocity. For Earth, it's about 11 kilometers per second. And one can calculate the escape velocity by comparing the potential and kinetic energy in the initial state and the final state. Initially, the potential energy is given by the gravitational potential, and the kinetic energy is given by the escape velocity. At the final state, they are both 0, and this gives us this value, which we can extrapolate to the relativistic case where classical mechanics or Newtonian mechanics is no longer applicable. Somehow it gives the exact answer. It gives the gravitational radius or Schwarzschild radius A that depends on the mass of the black hole m like this, and G is Newton's constant. In classical gravity, the correct way to derive this formula is to use geometry of space-time. The proper time, it's an element of length on a trajectory can be expressed like this. And this expression involves the gravitational potential. Now, we have to use the full theory of gravity, Einstein gravity. And its solution for a spherical symmetric body was found by Schwarzschild. It's given by this metric. The metric has some part that depends on time, the time component of the metric, the spatial component of the metrics, and there are actually two components, the radial one and the angular one. D omega is the angular element. The function f is given by this formula in 4 dimensions. In other dimensions, the formula is slightly different. To understand it better, we can consider the Euclidean version of that metric, or we can consider imaginary time. Instead of minus dt squared, use plus d tau squared and write the same formula. And this is a Riemannian metric on some space. It has an apparent singularity at r equal to a, the gravitational radius, but it's only an apparent singularity. We can introduce this coordinate in the vicinity of that singularity and resolve it using an analog of polar coordinates. So the imaginary time tau is kind of like the polar angle. And at the horizon, when r equals a, the circle of time vanishes. It shrinks down to a point, but nothing drastic happens actually. It's just a singularity in the coordinate system rather than in the space-time itself. In Lorentzian time, the picture is similar. One can define lines of constant r. These are green lines and lines of constant time, the blue lines, and one can map the Schwarzschild metric to a metric in this wedge. This wedge doesn't cover the whole space, unlike the picture on the left. It only covers a part of the space. And there are polar coordinates, but hyperbolic coordinates, actually. They use sinh and cosh instead of the sine function and the cosine function. And in the new coordinates, the metric is smooth. The new coordinates allow for extension. One can define an extended space-time, and it's called eternal black hole. This extended space-time is valid in an idealized situation when we have a black hole that existed forever and will exist forever. It doesn't change, and we may think of the space-time continued to some regions that are physically inaccessible. There is a region past the future horizon. This unlucky guy fell into the black hole, and he will cross the future horizon. By itself, crossing the future horizon is not a disaster, but then everything that passes through the future horizon falls onto a singularity, which is really bad. From outside, we don't see the horizon, let alone the singularity. And theoretically, one can think about other regions that are even more elusive. An important feature of the extended space-time is asymmetry. There is a symmetry that stretches everything in one direction, in the direction of the past horizon, and squeezes everything in the direction of the future horizon. And that symmetry acts on the full space-time. It acts somehow outside at large distances from the black hole, and also in the vicinity of the horizon. And one can define a parameter called surface gravity in the following way. In the vicinity of the horizon, this symmetry transformation acts as a Lorentz boost. And at large distances from the black hole, it acts as a time shift. If we divide a Lorentz boost by the time shift, we get something inversely proportional to time. And that's called surface gravity. If we multiply it by the speed of light, we'll get acceleration. And we may interpret it as the acceleration of free fall at the horizon. So this is an important parameter characterizing a classical black hole. But it's related to quantum mechanics of black hole, Hawking radiation. Hawking discovered some 50 years ago that black holes are not exactly black. They can emit radiation. They can emit photons and other particles. Most of those particles fall back down to the black hole, but some of them escape. And the radiation is characterized by temperature. It's like thermal radiation with a certain temperature related to the surface gravity. This formula has the Planck constant in it. It illustrates that the effect is quantum, but in most places, I set the Planck constant to 1 because we focus on quantum mechanics more than on classical mechanics. You can see that the radiation originates at the past horizon, and most of the radiation falls back through the future horizon. Some radiation escapes. One motivation for the SYK model was an attempt to reproduce the Hawking relation between the surface gravity and the temperature. This is a very simple relation, but we would like to reproduce it in a more conventional quantum system, not referring to black holes which are not well understood. The full understanding of a black hole perhaps requires string theory or some other advanced theory. And finally, I would like to discuss another effect for black holes, the Dray hoof effect. incoming particles, like if we throw something into a black hole, interact with Hawking radiation. And the interaction depends on the time interval. If we throw an object into a black hole, wait for some time t, and try to detect a Hawking radiation particle after that time t, the interaction between the incoming and undergoing object is amplified in time. This is counterintuitive. The interaction can become formally arbitrarily large. There are some limits on the interaction strength, of course, but one can think in details how one could observe this effect. This is the description of the effect in more detail. We throw a particle into the black hole, it creates some gravitational interaction, gravitational perturbation around the particle trajectory. And then we watch outgoing particles. And when we consider an outgoing particle at time t, it makes sense to apply the symmetry transformation such that the outgoing particle has a simpler description, a more natural description. But when we apply that symmetry transformation, we stretch everything in this direction and squeeze things in the opposite direction. And that makes a difference. The perturbation is concentrated near the path horizon, this purple line. And the perturbation looks like a shock wave, like a singularity in space-time. Although it's not a singularity, it's just a strongly squeezed, smooth space-time. And the radiation passing through this shock wave is delayed. This is the Dray hoof effect. How do we observe it? The observation is difficult because the shift, the outgoing particles experience is relative to the black hole interior. To actually detect this shift, we need a reference point inside the black hole, which is difficult. And this is similar to the butterfly effect. When it rains, we don't know whether it's due to a butterfly or not, but to make sure, to be sure that the rain is due to the butterfly, we need 2 copies of the system. And here is a potential scheme to observe the Dray hoof effect. We send a test particle to the black hole, but we send it the wrong way, back in time. That particle goes inside the black hole. Then we run the time forward, and while running the time forward, we drop an object into the black hole. This object creates a shock wave, and when the particle comes out of the black hole, it experiences a delay passing through the shock wave. And this way we can consider the difference between the initial state of the particle and the final state of the particle. In quantum mechanics, this effect is described using out-of-time order correlators. Now let me introduce the SYK model. It doesn't look like anything similar to a black hole. The model consists of Majorana degrees of freedom, chi1 through chi-n, which interact with each other using this quartic Hamiltonian. This model was first defined by Sachdev and Ye, but they defined it in a more complex way. And if we want to study more complex properties of this model, like out-of-time order correlator, it will be convenient to simplify the model first. And that is the simplified version. Detailed calculations in this model were done by Maldacen and Stanford and by Sach and myself. And this simple quantum mechanical system has a collective mode equivalent to Dray hoof shock waves, but in 1+1 dimensions. This is a formal description of Majorana fermions. Majorana fermions are generators of a Clifford algebra. These are the defining relations of Majorana operators. One can consider representations or the representation of this algebra using the Fock space, and one can express the action of chi j in terms of the action of lowering and raising, or annihilation and creation operators. And this is an illustration. When we apply a creation operator, we put a particle in a box, and we apply another creation operator, and we put a second particle in another box. The full definition of the SYK model is here. It's a quartic Hamiltonian, and it has random constants, random interactions. The average value is 0, but the second moment is not 0. It scales like 1 over n cubed to have a nice thermodynamic limit. And the randomness helps to solve the model. One can consider similar models with some specific interactions. They will be difficult to solve, but the random model is easy to solve. Now, let me mention some interesting properties of the SYK model. The first property is fast dynamics at low temperature. And that is why other models, many other models don't work. When we consider models like interacting spins at high temperature, the dynamics is slow because it's determined by the interaction strength rather than the temperature. Fast dynamics means that its speed is determined by the temperature. When we go to low temperatures, the system forms a so-called spin glass, and the dynamics is exponentially slow. There are other models like Fermi liquids, which have slow dynamics at low temperatures, but not exponentially slow, only quadratically slow. The SYK model is special because it's a non-Fermi liquid at low temperature, and that was the great insight by Sachdev-Ye in 1992. And I used this model and studied it in a slightly different direction, calculating out-of-time order correlators. The model is solvable for large n, and this is the exact interval of parameters where the model is exactly solvable. It has emergent symmetries at low temperatures and large n, and it has an approximate diffeomorphism symmetry, diffeomorphisms of a circle that is broken to the group of Möbius transformations, preserving the circle. And the symmetry breaking is both spontaneous and explicit. There is no explicit symmetry breaking at 0 temperature, but at any finite temperature, the symmetry is also explicitly broken. And the low energy states are described by this co-set. And in this co-set, we can define a collective mode that turns out to be equivalent to two-dimensional gravity. Now let me go through a few very technical slides. This is how the SYK model is solved. It's solved by using Feynman diagrams. And one can consider the full green function and the bare green function and interactions. And the dotted line means averaging over the Gaussian distribution of interactions. One can consider various diagrams and select leading diagrams. Some other diagrams also exist, they are suppressed by negative powers of n. If we write down the diagrammatic series only including leading diagrams, it has a special structure. This diagrammatic series can be written like this, and it's already transformed slightly. I use thick lines, which include a bunch of other diagrams with thin lines. Each thick line is the sum of many diagrams. The thick line is the full green function. Then the diagrammatic series is just the geometric series with sigma given by this, and there is actually a formula. And summing up the geometric series results in the Schwinger-Dyson equation, which should be combined with this equation. And these are just functional equations that can be solved on a computer. And one can obtain a solution graphically. One can calculate the green function. But at long time intervals, a solution can be obtained also analytically. And the trick is that one term in the Schwinger-Dyson equation becomes small at low temperature. The time derivative in the Schwinger-Dyson equation may be neglected at 0 temperature. And that gives the formula for the green function at 0 temperature, first obtained by Sachdev-Ye. And one can extend it to small but finite temperatures. But the most remarkable feature is the existence of a soft mode. If we look at the Schwinger-Dyson equation, neglecting the derivative term, then the solution is not unique. There are many solutions. If G is a solution, then we can construct a new G, which will also be a solution. And to do that, we change the time by an arbitrary function of f. Here I'm using the imaginary time formalism. The time goes around a circle, and the length of the circle is the inverse temperature, called beta. So there are multiple solutions. Each such solution is obtained from the 0 temperature green function, beta equals to infinity, by a certain transformation. And in particular, if this phi of tau is taken simply as 2 pi over beta times t proportional to t, we get the finite temperature solution at equilibrium. But there are many non-equilibrium solutions, and there are also fluctuations. At equilibrium, one can consider a fluctuating function phi, which may be thought of as a spring of time. There is this time circle that goes around, and its deformation is described by the function phi of tau. It's a map from the circle to itself, and there is an associated energy or action that involves the so-called Schwarzschild. The Schwarzschild is remarkable because if f is a linear fractional transformation, the Schwarzschild vanishes. It has certain transformation law under fractional linear transformations. And one can go even further. One can relate the Schwarzschild action to geometry. One can consider an unrelated question, a seemingly unrelated question. Let's consider a curve in the hyperbolic plane. This is the hyperbolic plane in the Poincare disk model. It has radial coordinate r and angular coordinate phi. And we consider a curve that is pretty close to the asymptotic boundary of the hyperbolic plane. And it turns out that the extrinsic curvature of this curve in this limit, when the curve is very close to the asymptotic boundary, is related to the Schwarz chain. And this way, we can reformulate the Schwarz chain action in purely geometric terms. We have a curve in the hyperbolic plane. It's kind of like a balloon filled with air. And there are two terms in the effective action. There is an area term, or the volume of air in the balloon. And there is also length. But the length can be kept fixed. The balloon cannot be stretched. And its energy will depend on the volume or the area. And now let's consider thermal fluctuations of this balloon. It can shrink in some directions, expand in other directions. And the statistics of these fluctuations is exactly the same as the statistics of the SYK model at low temperatures. One can make an analogy to the Lorentzian signature by passing from the hyperbolic plane to the anti-de Sitter space. Now the time is real, not imaginary. This coordinate phi may be interpreted as time, but it's not the physical time. The physical time is given by these green lines. Each green line is a line of constant radius going forward in time. And each blue line is a time slice. And in this interpretation, we can talk about the butterfly effect by considering two trajectories. One trajectory on the right and the other trajectory on the left. And in this picture, those trajectories are aligned with each other. We can use the left trajectory as a reference, and we can perturb the right trajectory. And when the right trajectory is perturbed, we have some exponential growth of perturbation, and that is classical chaos. Of course, the model can also be quantized, and it will be quantum chaos. And that's the origin of the connection between black holes and the SYK model. Finally, to clarify this connection, I should say that we have talked about boundary effects. These particles going in the anti-de Sitter space are boundaries of some space-time. And we can consider an actual theory of gravity for the bulk, for the space-time itself. But such a theory in 2 dimensions is degenerate. To make it non-degenerate, we need to introduce a new field, so-called dilaton. And qualitatively, it becomes similar to the Einstein theory in 3 space-time dimensions. However, this theory, as well as the Einstein theory for n equals 3, is rigid. It means that the bulk space-time is rigid, and all degrees of freedom are actually on the boundary. If we want to discuss the Dray hoof effect, we can apply some gauge transformation, some diffeomorphism that removes the shock waves and turns them into a deformation of boundaries. And this is the connection between gravity and the SYK model. So if we go the full way, we start with the SYK model, solve the Schwinger-Dyson equations, identify a collective mode, describe it geometrically as a boundary problem, and do some geometric transformation to turn into a bulk problem. And that bulk problem turns out to be a gravitational theory, although a very simple one. It's the so-called Jakif-Tatel-Boehm theory. So I've reached the final slide. Let me summarize. Chaos is a theoretical concept. Direct experimental tests of chaos are possibly only for very small systems. Quantum chaos can be described by out-of-time order correlators. The Lyapunov exponent is well defined in the quantum case in certain cases, in particular for large N systems and for black holes. To define the Lyapunov exponent, we need some large or small parameter. And these are two examples where such parameters exist. The SYK model is similar to black holes in that the Lyapunov exponent is as large as possible. It's equal to 2 pi times the temperature. And finally, if you think that out-of-time order correlators are completely irrelevant to the real world, let me describe a related model, which was introduced by Maldacena and Chi. It's two coupled copies of the SYK model. And the calculation of ordinary correlators in this model is similar to the calculation of out-of-time order correlators in a single copy of the SYK model. And the physical properties of this model are remarkable. This model exhibits quantum teleportation. If we introduce some perturbation on the left, we just knock the system slightly. The perturbation seems to be gone. It kind of dissolves in the many degrees of freedom. And after a certain time period, it emerges on the right. And one can think of this process as the system secretly having some bulk that is not seen in the picture on the left. And the perturbation propagates through this bulk from the left to the right and finally emerges. And it can bounce back and appear on the left again. So this theoretical exercise of calculating out-of-time order correlators can lead and have led to new discoveries that may be possible to test experimentally in the future. Thank you for your attention.
Well, thank you for the great talk. Let's now have questions. Oh, there.
Thanks so much, Professor Kitaev, for this wonderful talk. I really enjoyed it. So my question is about, is it possible to implement the first test of the butterfly effect that you mentioned earlier on a quantum computer? And maybe more specifically, suppose we are able to construct a quantum circuit and simulate the forward and backward time evolution of certain many-body quantum systems, and then and we can suppose also ignore the potential errors from Schroeder product formula and the coherence errors from simulation. Then can we expect how large the system is going to be to make the test work, and which kind of quantum operations could be treated as a butterfly in the simulation? Thanks.
Yes, it is possible to simulate that on a quantum computer, and it has been done in a small system with a few qubits. The gates that were applied were randomly chosen. One can choose random gates, not even using a Hamiltonian or Trotter approximation. One applies a sequence of gates, then some entangling gate, and the reverse sequence of gates. That has already been done.
Other questions? Other questions? Yeah.
Thank you for your beautiful talk. in the spectral theory, the quantum chaos describes the eigenvalues and eigenfunctions of high frequencies on the chaotic space. I want to know the large N particle system, and are there some relation between the large N particle system and the chaotic dynamical system, like the geodesic flow on hyperbolic surface? Thank you.
I'm not sure if there is an exact relation, but there is an analogy. For large N systems, 1 over N is analogous to the Planck constant. It would be nice to have a closer analogy, but I don't know how to do that.
Oh, thank you.
Okay. Other questions?
So there are similar solutions from classical consideration. If you slide inside the horizon, and the solution is not smooth, and the mathematicians can prove there are shock waves in time, but not smooth. So maybe, this phenomena can be understood with large N. So it's actually a classical phenomenon.
Do you mean classical shock waves like in a gas, or do you mean gravitational shock waves?
Yeah, so the solution is not smooth, but it has shock waves in time.
Do you mean shock waves in a gas or in a different system?
Just inside the black hole. Horizon.
Inside the black hole.
Yeah, horizon.
Yeah, you can find a solution that is not smooth, but classically, the solution appears asymptotically by the evolution of a smooth solution, and the singularity does not develop at any finite time. This is just a property of Einstein's equations.
Okay, other questions? Yeah.
Okay, thank you for the talk. I have a question on the quantum chaos on the continuous symmetry. I'm working on math problem calculating the so-called OTOC on the toy model of black hole, the so-called hidden particle protocol, on the continuous symmetry or maybe conservation law of groups like the U1 or SUD group. But I'm always wondering, is it proper to ask such a question in the sense of physics, because maybe from the perspective of ADS-CFT and the problem to have global symmetry on black hole. So I'm wondering, is it proper to ask this question from physics? And do we have any other interesting physics model to consider on the maybe continuous symmetry, like maybe the SYK model you mentioned? Thank you.
Excuse me, I didn't understand. You asked about whether it's proper to ask some question. What is?
Yeah. I mean, because when we consider the hidden particle, we always calculate the OTOC on the dynamics with no symmetry. But now I'm hoping to ask, could we do similar things when we have continuous symmetry imposed on the system? Yeah, the symmetry of the from some group like the U1 group or maybe SUD group.
There are variants of the SYK model with symmetries. In particular, the complex SYK model has a U1 symmetry corresponding to the conserved electric charge.
Okay, we have to wrap up. So thank you very much for the beautiful talk.